Yes.
Yes, we can hear you.
Yeah. Yeah, I was actually a TA at Neuromatch, and it was a lot of fun, and I learned a lot. Even though I was in a teaching position, it was still very enlightening to have gone through all of those tutorials and actually doing all of the techniques. I'm very thankful for Neuromatch. Mhm. Yeah, it could be better. It's like I'm seeing numbers like 55–60% of people are actually wearing masks, and it's you do what you can. I'm in the northeastern part of the United States in Philadelphia, and it used to be, especially with New York City, that the numbers were very high in that part of the country. But now the more southeastern states are really dealing with high cases of the virus. So yeah. So my hope is that we're able to bring it together sooner than later, and hopefully fight this thing off. How is it over there? Mm-hmm. Mm-hmm. Yeah. It must be very hot over there right now. Is it? Mm-hmm. Oh, I see. That makes sense. Um, mhm. Is there a way to
Hi, everyone.
handle? Oh, hello.
Hi, Ilenna. Hi there.
Hello. Amartya and Mohit.
Yeah.
Okay.
Yeah.
Is there a way that we'll be handling questions, or will those be at the end of the?
I think we can keep it for the end if it's all right with you. I guess. Then you can the talk can be fluent, without any interruptions. So I guess that will be nice.
Mm-hmm. Okay. So should I just start?
Maybe we can take a couple more minutes. Let's see if if anybody else joins, and maybe we can start. So 2 more minutes, and we can start then.
Sounds good. Maybe, yeah. One thing that is nice about being home is that I get to be able to, everything's more connected in a way. I'm very thankful that I was invited to present at Sign. I don't think that would have ever been possible or believed to have been possible before the pandemic. So there's silver linings everywhere, it seems.
Exactly. The sign was actually born out of the necessity. The pandemic forced this kind of situation, and I think everybody around the world is just trying to, make something out of nothing, and sign is just an example of that. So yeah.
Mm-hmm. Yeah, just like Neuromatch.
Exactly.
My understanding is that Neuromatch 3.0, the outside of the academy, the conference, is going to try to happen where SFN was originally going to happen, and try to open up to all parts of neuroscience. And I'm pretty excited about that. Hopefully, you all can, join in on that fun present.
Definitely. So then, I think we can start if that's all right with you.
Mm-hmm.
All right. So yeah, the stage is yours.
Okay. Just let me get the technical things together. And presenting. Can you all see that?
Yeah.
Yep.
Is it okay? So it's just the slideshow, not presenter view.
Yeah, it's just a slideshow. Yeah.
All right, great. So without further ado, my name is Ilenna Jones. I'm a fourth-year PhD candidate in the neuroscience program in Professor Conrad Korting's lab. And today I'll be presenting my work, which asks the question, can single neurons solve MNIST? And MNIST will become clear if you're not already aware of MNIST. I'll be explaining it further in the slides, but it's a particular kind of task. And I'll explain this further in these slides. So, what I'll be exploring is the computational power of biological dendritic trees. So, since neurons have been identified as the units of the brain that make up the brain, the question in neuroscience, what can a neuron do, has been a classic question and one that many people have tried to investigate. However, the question, what can a neuron do, is very vague in the word do. You could define do in terms of the neuron's role. What do neurons do to mediate behaviors? You could have neurons that are defined by their role in audition or the visual pathway. For example, retinal ganglion cells are named for their role in the retina and vision. So that is one way to define do. But you could also define do in terms of the neuron's computational capability, where you consider a neuron as an input-output device, where the input is going to be received at the dendrites of the neuron. This input current then is integrated into the trunk and soma of the dendritic of the neuron, and then the output of the neuron is going to be represented as either a subthreshold voltage change or a action potential, or the absence of an action potential. So one way of thinking about the output is that it is binary. I'm not the first to approach a neuron as an input-output device. In 1943, McCulloch and Pitts, who are some of the first computational neuroscientists, produced a computational model of a neuron, which is the McCulloch and Pitts neuron, where it is literally a linear weighted sum of its inputs and then put through a threshold nonlinearity, so that the sum of this is mapped through a nonlinearity such that the output is going to be binary, 1 or -1, or 0 and 1, as long as it's binary. So fast forwards, and and these neurons can be placed one after another in order to create logic functions and, or, and other logic gate functions. If you fast forward 70 years, you can actually find these configurations of neurons hooked up, thousands of these neurons hooked up in succession to form artificial neural networks in the deep learning field. And rather than just simple logic functions, they're able to perform even more complex tasks, such as high-dimensional image classification, where images can be considered high-dimensional because every single pixel value is every single pixel in an image is a dimension. And so high-resolution images, such as an ImageNet, a data set of images with their labels of what is in the images, can be then fed into a neural network like this one here, Krzyzewski's neural network, AlexNet. And this network is then able to take an image and then classify what is in the image. So for example, if it's an image of a container ship, it might say, oh, it's likely a container ship, maybe a lifeboat. Also slight chance it's an amphibian, but probably a container ship. So, however, the Macaulay-Pitts neurons and the artificial neural network neurons are linear weighted sums of inputs mapped through an output nonlinearity. I want to emphasize that they are linear weighted sums of inputs, which follows the point neuron assumption. We know that dendrites are these intricate branched morphologies where the inputs go through these the dendritic branches that combine to lead to the soma. But if you consider that these branches are linear, then you can represent all of these inputs as if they are simply going directly to the soma. And that basically means the reason why it's called a point neuron assumption is because the dendrites are basically, the shape morphology of the dendrites are basically non-important. You may as well have a neuron that is a point with no branches. So that's what it means to assume that the dendrites are linear. However, based off of a wealth of empirical work, dendrites are known to be nonlinear. So even within the dendrites, you can have logical operations. For example, if you have an excitatory input followed by an inhibitory shunting input, you can have a logic function which is A and not B. So a current flows through this dendrite if A is active and not B, and so on. You can also have coincidence detection, where if an action potential, where you can have the incorporation of a back-propagating action potential, which is a very cool dendritic dynamic where if an action potential happens at the soma of the neuron, current actually flows backward up through the dendritic tree, and this can actually trigger dendritic calcium spikes within the dendrite. So spikes don't only occur, sodium spikes occur in the soma, calcium spikes can occur in the dendrite. And these dendritic calcium spikes then lead to a current flowing back down to the soma and triggering a bursting activity. And you can also have, because of attenuation as the current flows through the dendritic tree, you can get low pass filtering and more. So all of these dendritic computations, or rather dynamics, they just illustrate that neurons cannot really be point neurons, and that point neurons may be grossly underestimating what neurons can do. So how do we ask what neurons can do? For this, we can turn to neuron modeling. And I'm going to talk about two methods of neuron modeling, a more traditional method and a method that I'm proposing. So the traditional method is the empirical neuron modeling procedure. And so this is where you, if you were to have an input current and that you yourself know, and input it into a real neuron in vitro or in slice via an electrode, you can then record the output of that neuron, the voltage output of that neuron, which could be represented as the spike train with, in addition to subthreshold voltage change. And that is your empirical recording. So if you take that input current and put it into a parameterized mathematical neuron model, that mathematical neuron model can produce an output. Usually the neuron model is randomly initialized, where its output will also be random. So what you need to do is then optimize your neuron model and change the parameters of that neuron model until the model outputs a voltage trace that is equivalent to or close to the empirical recording. So basically your empirical recording matching through some sort of training or optimization of your neuron model. And where your input is current and your output is your known empirical recording. And when you have this matching of computational output to empirical recording output, then it is considered that you have a good neuron model. And this is very useful because then you can take this neuron model and then test counterfactual conditions, as well as make predictions about what the original neuron that the model is modeled after, and make predictions as to what that neuron may do given certain situations, given certain kinds of input. So the second procedure is guided by this question. Like with artificial neural networks, can we test a neuron's ability to perform tasks? Going back to the slide that I showed you of the artificial neural network, AlexNet, it did a high-dimensional image classification task. This is the type of task that I'm talking about, where it's doing some form of classification task. Can a neuron do that? So I call this a task-based neuron modeling procedure, where if you put the empirical setup side by side with the task-based setup, you can see that the input is, instead of it being a somatic current input, or you could even do a dendritic current input if you are so skilled and are able to put an electrode in a dendrite. But you could have a dendritic task input, where the task input is high dimensional, which means that there are many, many inputs, synaptic inputs into your model. And instead of the target output being an empirical recording, the target output can be a correct classification of your task input. If you're thinking about image classification, you can say that the task input of a certain class contains a particular pattern or a particular kind of information that is relevant to its correct classification. So what the neuron model will be doing is then learning an input-output function where the input is an image and the output is a correct classification. Can a neuron do this task? And reasons why we do this is we can take a principled approach to setting what the numerous dendritic inputs are, and we can also quantify the neuron model performance via an accuracy measure. The neuron is either going to be correct in classification or incorrect in classification, allowing us to do some sort of accuracy measure. So what is the task that I'm talking about? The input-output. It's a binary classification of images, where I want to focus you to the top row, which is going to be MNIST, and I call it binary. I assert that it should be binary classification if you consider the binary nature of a neuron. It either creates an action potential spike or there's an absence of an action potential spike. So I'm considering it being binary. So MNIST, if you're aware of MNIST, you should know that MNIST is a data set of images of handwritten numbers. And these numbers go from 0 to 9. So there's 10 classes. I modify MNIST by only choosing 2 of those classes and then making it the task such that the neuron model should then receive an image from each of those classes, one at a time, and then classify whether or not that image is the target class. So, for example, if 5 was the target class, if it saw an image of a 3, it would return 0, and if it receives an image of a 5, it would return 1. So how do I know which classes to choose? Well, I basically took every pair of classes and tried to find which ones were the least linearly separable, or the 2 classes that were most confused between each other. And I used a linear classifier, linear discriminant analysis, to do this. The pair that received the worst classification score, I chose for this task. And I did this for multiple data sets, not only MNIST, but Fashion MNIST, eMNIST, Kuzushiji MNIST, CFAR10, Street View house numbers, and USPS. These data sets differ in terms of their content, but also their input size. So these 4, MNIST and the 3 on the bottom left, are 1024 dimensional if you turn them into a 1D array. And the CFAR10 and Street View house numbers are larger. They're 3072 dimensional. Because they're 3-channel 32 by 32 images. By the way, I didn't mention the MNIST and the 3 on the bottom left are originally 28 by 28, but I padded them to be 32 by 32. And USPS is very small. It's 16 by 16, making it a 256 1D input. So we know what the input-output task is, where the image is the input, the class is the correct classification of the class is the output, where the output would be 0 or 1. What about the neuron model that I am using to learn this input-output function? The neuron model that I chose is the one tree, and I chose it with a particular purpose in mind. So if you were to take this cartoon neuron, which is receiving 4 inputs on its dendritic tree, if you were to consider that each branch were a compartment of the tree, you can say that each compartment only receives 2 inputs. And that creates a binary tree structure, and that is a property of a dendrite. So what I decided to do was take a deep neural network architecture and impose upon it this dendritic sparsity constraint, where the deep neural network must be a strict binary tree with that particular ordered sparsity. And each compartment or branch of the neuron model is a nonlinear node that is typical of a deep neural network, allowing for the neuron model's tree structure to also have nonlinearities. I do not mean to say that the nonlinearities are the same as that in a dendritic tree. They are nonlinearities that are typically used in a deep neural network, particularly Liku-ReLU is what we used. So why do I do this? It's because the deep neural network is able to perform tasks. It has we've got a loss function that works with it, an optimizer, and I'm able to do backpropagation with this model. So I know that it is able to then be trained to do a particular task. What I'm trying to learn is what the impact is of dendritic sparsity. And so basically I'm taking a very abstracted model and imposing it a biological property in order to learn what the impact of that biological property is. And that might give me some insight into what the impact is of this biological property is on a real neuron. So what I do is then for my experiment is to compare. I can take this one tree and determine its accuracy in a binary classification image classification task. And I can compare it to a linear point neuron model. What we do in particular here is we're going to use a proxy for a linear point neuron model, specifically linear discriminant analysis, but I'll be calling it a linear classifier because it is. And also comparing it to a fully connected neural network that is 2 layers. It's 2 layers and it has a particular structure in order to be parameter matched with the one tree, which is very sparse and has a lower amount of parameters than a typical neural network. We expect that the fully connected network should perform better than the one tree, only because of our awareness that a 2-layer neural network can work as a universal approximator, and we also expect that the one tree should perform better than the linear point neuron model because its nonlinearities should have some impact on its expressibility of certain kinds of functions.
Ilenna?
Yes.
If I may, what does the 1 in the one tree mean?
Yeah, so 1. So it'll become clearer later on, but 1, you can say that, and by the way, can you see my mouse if I move it here?
Nope. Okay,
so I will move it here.
Yes, I do. I see it now. I see it now. Sorry.
Yeah, so I have to look at the other screen to see my mouse. So you've got a subtree in this dendritic cartoon of what you could maybe call it a stellate cell, because stellate cells have dendritic subtrees all connected directly to the soma. And this is one subtree of the dendritic tree as a whole. And that's why I call it a one tree, because it is one tree, one subtree, that is. It'll become clearer, it's like, but what about 2 tree? Well, that'll become clearer further on in the presentation.
Okay.
Great question, thank you. So I'm gonna look at the other screen in order to make sure that my mouse can guide. So this is a fairly busy slide, but I want to direct you to A. So A is a accuracy plot where in the x-axis I have labeled the one tree, linear discriminant analysis with a linear classifier, and FCNN, the fully connected network. And y-axis is accuracy, and this is for the MNIST data set. And the one tree performs better than the linear classifier as expected, but worse than the fully connected network, which is also expected. And this is also seen in B, C, and D in a pretty reliable way. And then in E and F, the one tree and the fully connected neural network perform about. See, it's actually quite low. And if you'll recall from binary classification, chance, just random guessing by the network should be at 50%. So this accuracy is actually quite low. And what we did here is that certain, for the deep learning models, there's a chance of there being failure to train, which leads to a performance that is close to 50%. So we actually had a threshold cutting off failed trials, but some trials that are failed may not have been cut off by that threshold, leading to this very large variability in both deep learning models. And so I would say that this result is actually, I cannot say that this is a conclusive result, same with SVHN, due to the high variability of the two deep learning networks, because they may be including failed trainings that are close to 50%. It's similar to the USPS comparison. A failed trial close to 50% can lead to such a large variability, going from 60 to 90%. It's a huge variability. It might include some failed trials, leading to it being pulled down lower than even the linear classifier in the fully connected network. So, but that's for full transparency. What the takeaway is for this slide is that even if you are to, I feel like one of the takeaways for this slide is that if you are trying to understand what a neural network is able to, how a neuron is able to perform tasks, you probably should not use fully connected networks to approximate what a neuron can do, because a fully connected network is going to not reflect accurately negative impact, or rather the constraints that tree sparsity does, which is an actual property of neurons. If you're going to try to use neural networks to approximate what neurons can do, it's important to include realistic properties that might negatively impact the performance of your model in order to stay within the realm of biological realism. I will say, if anyone out in the audience is aware of machine learning, we're not trying to show that this biological property will improve machine learning algorithms. What we're trying to learn is what the impact is of this biological property on performance in order to better understand what the neuron is capable of.
Ilenna, I have
Yes.
a quick question. So, is there a reason why the error bars are bigger for the LDA and the one tree as opposed to the FCNN?
Are you talking about A?
Yeah, A, panel A, let's say.
The error bars. So it's, are you talking about A, or, because
yes, with MNIST.
Yes, so the one tree seems to have a larger error bar than the linear classifier, so I'm not exactly sure what your question is.
No. So do these correspond to sort of like different initializations, or where's the, for example, with the LDA, as I understand it, if the architecture is fixed and you have, let's say, the same number of weights, you can sort of optimally solve it, right?
Yes.
So the okay, so presumably this is with respect to different sort of cross-validation runs of the network. Is that right?
Yes, exactly. And Yes, and we ran several trials, up to 10 trials for the linear classifier, one tree, and FCNN, and it would be less than 10 trials, down to at the very least 7 trials for all of these conditions. So n is equal to 7 to 10 for all of these.
Okay. No, so I'm just wondering that is it because you perhaps ran several more of the FCNN as opposed to LDA and one tree, or is it just, is there something deeper in the variability being more?
Yeah. So if I remembered correctly, so the one tree actually has about 8 samples. The LDA has 10 and the FCNN has 10. So 2 of the samples did not train. They actually, basically you'd have like stuff like 92, 91, 93, and then 50, 51.
Okay. Mm-hmm.
So the trials that failed so catastrophically were removed, such that, because otherwise you'd have something that looks kind of like this. I used one single threshold value across all of them, as opposed to picking which ones were failing and then deciding not to include them. So yeah, so there is the variability is going to be resulting from 7 to 10 trials that are included in each of these.
Okay.
Mm-hmm. Thanks for your question. So we see that with the sparsity constraint, performance of a deep learning network decreases. And this sparsity constraint is what neurons have. So what else can impact single neuron computation, or this deep learning neuron model computation? So we know, let's look at some of our givens. Neurons have thousands of synapses. And presynaptic neurons synapse approximately 4 times per postsynaptic neuron, which means that any neuron will have approximately 4 repeated inputs from a presynaptic neuron. And we also know that in vitro multisynaptic batons into the same dendrite. So multisynaptic batons are basically repeated inputs. So they increase approximately 6-fold after an LTP, or long-term potentiation induction protocol, which leads us to conclude that learning, which is how we're interpreting LTP, learning may impact the replication of synapses. So that leads us to leads me to the hypothesis that repeated synapses may also impact single neuron computation, since learning would be the means by which a neuron's computation would be able to change. So repeated synapses may also impact single neuron computation. How do we test this? We can modify the one tree to take repeated synapses. And going back to your question, why did we call it a one tree? Well, it's because of this step. So say you take your cartoon neuron again, but you're repeating the inputs 1, 2, 3, 4 across each of these subtrees. And then you represent that neuron with that many subtrees as a K tree, where K is equal to the number of subtrees in that neuron that is receiving those repeated inputs. So where K is equal to 1, you got the one tree. Where K is equal to 4, you get what we would call a 4 tree. But I call them K trees to remain general. What you can also observe is that the nodes for these trees remains such that the input to any one of these, there's only 2 inputs to any one of these nodes, but the soma node can receive k inputs, or as many subtrees as there are, the soma node or the output node will receive that many inputs. So we were comparing the one tree to a fully connected network of similar parameter size. We need to, if we're going to continue this analysis, we need to be able to adjust the parameter size of a fully connected network so that it approximately matches that of the K-tree. Because in deep learning, one of the rules of thumb is that the more parameters you have, the better the accuracy of the model. So we want to match that. So modifying the fully connected network, we can actually do that by changing the hidden. It's a 2-layer neural network, so we can change the hidden layer size to change the parameter size. So if you have, here's these expressions are equal to the number of parameters in each model. The K-tree model has n inputs and k subtrees, and its parameters size is equal to 2k times the n parameter of the 2k times the quantity of n minus 1. A fully connected 2-layer neural network has n inputs and h hidden layer nodes, and its number of parameters is equal to h times the quantity of n plus 1, where you can set these to be equal, these two to be approximately equal, by setting h to be equal to twice the number of subtrees the K-tree has. And that is what we did. So here's another busy slide showing the results. And I'm going to direct you to A again. So the x-axis of A shows represents the architecture K, where K is equal to the number of subtrees of the K-tree, and half the size of the hidden layer of the fully connected neural network. So, and I go from 1 to 32, doubling every time. And then I have the linear classifier point here as a point of reference. And gray is the fully connected neural network. Black is the K-tree performance, and Y is the accuracy. So what you can see here is that the K-tree performance increases with the increasing number of repeats in subtrees. And this can be seen approximately reliably as you go to other tasks. In gray, you also see an increase as you increase the size of the fully connected network. Performance also increases. So this increase in the K-tree performance could be due to just the parameter increase, but also the number of repeats. And these two, you can actually see that the K-tree, however very different when there's one subtree, actually approximates or approximately approaches the fully connected neural network as you increase the number of subtrees. And in the case of the fashion MNIST, eMNIST, and USPS, the 32 tree, where k is equal to 32, is indistinguishable from the fully connected network, such that if you were to do a t-test of the performances at that particular parameter, they are not significantly different.
Ilenna, can I interrupt
yes.
one? Can you comment on the CIFAR-10 comparison? Because the FCNN accuracy drops in that case, and I think that's the only plot here which shows
Yes.
that. Yeah, okay.
Definitely. I was going to say that that's not the case with KMNIST and SVHN, but the CIFAR-10 is very interesting because the fully connected network performance does decrease with an increase in the hidden layer size. And I would note that the variability, the standard error does not explode as this goes down, which leads me to believe that the thresholding, the failed training thresholding problem is not the case here. The performance is actually going down with a decrease in hidden layer size. And it may be this idea that, like, I'm not exactly sure why. I can probably guess that there's something about the hidden layer size that does not jive very well with this very high dimensional image classification task, where there's 3 channels that's represented in this in these images. One of the reasons why we try all of these tasks is because it's because of the no free lunch theorem. If you have a algorithm that does particularly well with one task, it can actually perform much worse in other tasks. And I feel like this is a classic example of that kind of thing with the CFAR10 example. But I cannot necessarily say exactly why, given the nature of the models we're using. But what happens with the K-tree is that it actually performs better at this than this decreasing fully connected network performance. Now, if the fully connected network did what we would expect it to do, which is to, increase, then that might not be the case. So,
Ilenna, if I may. Yeah. So at what point, which is to say, at what value of k does your K-tree neuron model become equivalent to a fully connected neural network?
So if I were to increase,
do so at all? Yeah.
Does it do so at all? So in MNIST, perhaps if we were to try k equals 64, maybe they would meet. But given, I feel like that could be something that I could try. Though this is the result I have so far.
No, so.
Yes.
Right. So, I mean, my question was sort of a bit different. So, I was wondering whether mathematically you could, at some value of k, that it would become equivalent to a fully connected network, in the sense that if I gave you, so let's say there existed such a k, right? So if I gave you a fully connected network, that you could come up with a K-tree neuron model for that particular k, let's say, for which you could reproduce any fully connected neural net that I gave you, right?
Yeah.
So I was asking, yeah.
Yeah, that's a really good question.
Yeah.
Mathematically, I feel like that would be a really cool expansion on the theory behind why I'm seeing the results that I do. And I feel like I would need to consult a deep learning mathematician. I know one, but currently that's outside of my skill set. But that may be the case that a K-tree, if you have a K-tree of large enough size, you might be able to approximate any fully connected network. Or maybe the alternate situation where because of the structure of the K-tree, there is a saturation point where the fully connected network can go beyond the K-tree, and as you increase, but or something. I'm not quite sure. I have these computational results that,
Right. So
yes.
the way I'm thinking about it is, okay, so if I understand your K, so K refers to the number of times that your inputs are repeatedly sort of, fed into the dendritic tree, as it were, right? Is that correct?
Mm-hmm.
Okay.
Mm-hmm.
So so let's say your fully connected neural network has M hidden nodes, where I refer to the white colored nodes as the hidden nodes. And in this case, it would seem to me that an M tree neuron model would be equivalent, because what you could do is simply to turn the sort of second set of nonlinear nodes into just linear nodes, and then just copy the weights from the fully connected neural net to the. Do you see what I'm saying?
I think so. So
Yeah,
if you were to take the if you were to take the number of subtrees, and since I keep moving on to the next slide. So since each of these nodes receives 2 inputs, if you were to increase the number of subtrees such that these nodes is equal to n, then it would be almost equivalent as, say, taking this node and receiving these 2, but having all of these different weights to adjust by. So
yeah, I'll have to think about it.
This is a cool way of thinking about it. I'll need to think about it too. I appreciate that. That's really cool.
Yeah. Thanks.
So the takeaways from this slide is that the K-tree performance does increase with an increase in K. And in some cases, at least in this 32 case, in some cases, it actually can meet the level of performance of the fully connected neural network. Now, it would be very interesting to follow this up, see if there's some sort of mathematical reason for why this is the case. And that could be future work. So some discussions and takeaways. I want to address the limitations and assumptions. A blanket statement that I can make about this project is that I'm taking a very abstracted model that is not a neuron model at all, and then imposing upon it a biological property, which is the dendritic structure constraints of a sparse tree structure, binary tree structure, and trying to learn what the impact is of that biological property. So as a result, there's many things that one can say that limits this work. So 1D vectorized image classification task does put our neuron model out of brain context. It is not necessarily the case that a neuron is going to receive raw pixel input from an image. That's not what neurons would actually see. Our model is an abstracted approximation to a real neuron. It's tenuous. It's not a real neuron. Neurons are not feed-forward like our model. Synapse location is not limited to the terminals of the dendritic tree like our model. And our neuron model is receiving real-valued inputs, not binary inputs. And given the feed-forward regime, binary inputs would make more sense if this was supposedly more realistic. I want to turn this on its head, though. Every assumption that I make about the neuron, this model that I have, can be a new future direction. If I were to make the neuron model that I have with its dendritic structure constraints, if I were to make it recurrent and time dynamic, if I were to place synapses anywhere on the dendritic tree, just not at the terminals, and if I restricted the inputs to be binary inputs, those would be steps toward approximating to a real neuron. But given what I've done, the takeaway is that dendritic tree structure constraints impact the computation of our deep learning model that is approximating a neuron. And repeated inputs does also have an impact on the computation that we're seeing. So some relevance to deep learning. This is a special case of sparse neural network. This sparse network can perform at the level of a dense network using nearly the same amount of free parameters for certain kinds of tasks. And some future work could be to compare this K-tree sparse network to other kinds of sparse networks, such as the randomly connected sparse networks with equal density to the K-tree sparse network, or even the pruned sparse networks that can be seen from the lottery ticket hypothesis paper. So some relevance to neuroscience. This is a new approach where we consider bringing deep learning approaches toward neuron modeling, where we judge neuron model performance instead of traditionally trying to match neuron physiology data. Neuron model performance on a task. So our results suggest that repeated inputs to a dendritic tree could improve its ability to perform complex computations. And this takeaway is I think, a message to neuron modelers, which is to perhaps consider the complexities and impacts of repeated inputs in your neuron models. And future work is to introduce more biological constraints on this already abstracted model, as I've addressed in the previous a couple slides ago, and also train biophysical neuron models to do image classification using this deep learning approach of task-based modeling. So with that, I thank the Coding Lab. Everyone in the Coding Lab has had some impact on this work through many, many conversations. I thank my advisor, Conrad Cording, and the Neuroscience Graduate Group and the University of Pennsylvania. With that, are there any questions?
All right. Thank you, Ilenna. Thank you. This was a very interesting and exciting talk. This is really nice, and I think the audience was engaged really well. So thanks. And yeah, any questions? I think we have got a couple of questions. So maybe Amartya can tackle that.
Yeah.
We have actually one question here. So someone has asked, what are the parameters here? So it was with respect to the slide. If you can go, like, can you turn on the slide? Like, So it was, I guess, with respect to the empirical neuron modeling.
What are the parameters with respect to empirical neuron modeling?
Yeah, like the parameters in which I think there was some spikes in like there was a slide where you show how to measure spikes and compared the empirical neuron modeling. So I think they want to ask what were the parameters and how did you guys measure?
So to clarify, so is it the parameters that my model uses or parameters that models use in general?
I think it's in general, like general, how to compare the model, yeah.
Yeah, so neuron models can take many, many forms, from anywhere to very realistic Hodgkin-Huxley models where they model the actual ion channel conductances in the neuron model. And it could be a point neuron with ion channels on them, or it could be a very morphologically complex, dendritically complex neuron model with ion channel conductances. And that can be what you have as a neuron model, and you the parameters for such a model would be, you know, what the density is of those ion channels. So how many ion channels you might have at any particular part of your morphologically realistic neuron. So that's like very realistic, and that's a type of neuron model you might have. You could also go to something as abstract as the Izhikevich. I'll type that into the chat actually. The Izhikevich neuron model, which is I hope I spelled it right. Which has, it's a very abstracted model that has some parameters that kind of correspond to various output properties, like that is not necessarily grounded in any realistic in realistic empirical content or realistic properties that a neuron actually has, that might also perform just as well as the detailed neuron model. So the neuron model determines what parameters you have, and the parameters that you have can correspond to realistic properties of the neuron or non-realistic properties of a neuron. And really, it's kind of like, whatever you want to learn about a neuron determines what kind of neuron model you use, barring, some sort of very hyper-realistic neuron model where you're trying to say, I'm trying to learn what a neuron can do, and then you try to make it super realistic, and then you say, this is what a neuron can do. But as we know, all models are wrong, but some models are useful. So it's kind of like, what do you want to learn is more so the question that you have to ask yourself when you choose your neuron model, which determines what parameters you have.
Ilenna, I have a question. So
Yes.
first of all, really cool talk, and thank you for taking the time, and thank you to Sign for sort of nicely arranging this. My question was the following. So, and sort of this is perhaps a big picture question. So if single neurons are so good, why do we have so many of them?
Right. Well, I feel like I wish I could find a picture of this. If they're so good, why do we have so many of them? Well, we've got TPUs in Google that fill up entire rooms that are used to train models that can barely do what people do, or can do what people do, but only that one thing. However, brains are very robust and can do many things, highly generalizable, can adjust in many different ways, and deal with very complex inputs, and have mental models of causal mental models of the world, and whatever the world throws at it. And I could probably just, I feel like that question is very good in that it gets at this idea of like, maybe we can just have, maybe we have so many neurons because they're doing very simple things. Well, what if our approximations to what the brain can do, fill huge rooms and require tons of data, and perhaps a brain which only takes the power of a light bulb needs so many neurons because every neuron is doing like such complex things. And so I guess this type of work, it kind of gets at this type of work and what the purpose of it is. And a way to think about it is that you can set a lower bound of what neurons should be able to do. And then I think the next step of this kind of work, or this line of questioning, is finding what the upper bound of what is possible for a neuron to do. And if you find that upper bound, you can then determine or make some general approximations of how many neurons would be necessary to do some complex task or behavior. And I'm not necessarily sure if we have much work by way of determining those upper bounds.
Right. So as I understand it, you're saying A, the tasks are perhaps more complicated, and B, we have many such tasks. Is that okay? Cool.
Yeah,
Thanks.
and the brain is very robust and generalizable. So it's and can do one-shot learning pretty quickly. You know, it's quite remarkable.
Thanks.
Okay, can I go next?
Yes.
So thank you for your talk, and thanks to Sign for preparing all of this. And my question is, when I see the title of your presentation, I thought, okay, cool. There is a way to classify like MNIST with a whole MNIST data set with only single neuron. And I was thinking that what possible approach could we use to tackle this problem, and I'm still thinking that if we add some more complexity of biological neurons to the problem, and we use those complexity, we still can some kind of encode and decode more classes of out of one single neuron, and those features that we can use for such a problem, it could be the frequency of activity of single neuron, or maybe, I don't know, maybe the delay of response of single neuron. I'm not sure if it's possible, or maybe you already tried it and I don't know, but that could be still a question, and I want to just hear your opinion about this.
Yeah, so what you're kind of talking more so about is the temporal dynamics of the output of a neuron, and how that might be able to kind of represent a particular correct classification of the full 10 class data set. Is that what you're talking about?
Yeah, that's right.
Yeah, so given one of the limitations of the work that I've done is that I've assumed that the neuron model, or the deep learning network that is approximating a neuron model, is feed-forward. And feed-forward output is, just singular output. It doesn't time vary at all. If I were to make this model more recurrent, and I would have to, and I could produce an output that is time varying. And then what the question is, how do you interpret that time varying output such that it corresponds to a particular class, and not just a binary classification, but a 10 class classification. And with that would require a bit more thought. It could be that, if the frequency is 0 to 1 hertz, or 0 to 1, firing within a particular unit of time, second or less, might correspond to class 0, and then more class 2, or more class 8, or even more class 10. So, class 9. So it seems a bit more, it is definitely a bit more complicated, and it does require more thought. But it's definitely a direction to go to see if, so that you're able to, I think one of the benefits of that line of thought would be being able to compare this model to other deep learning models, deep learning architectures. And, you know, now an easy way to do that, you know, without making it recurrent is to say, cool, stay feed forward, but the output, actually, I realized that, oops, sorry. You can take the output, and instead of it being 1 node, you make it 10 nodes. And then you've got some form of deeply, like a densely connected output layer that happens. And then you can say, okay, this sparse network with a densely connected output node, output layer is doing 10 class classification. So that would be another way to try, but it would go against this kind of tree constraint, which I'm trying to investigate. So it's like you need to think about like how to get around it so that it can perform certain kinds of tasks. Does that answer your question?
Yeah, kind of. So, I mean, basically, you're saying that it is a hard problem to do such a thing. And if you add some other neuron at the last layer, so it's not a single neuron classification anymore, right?
Mm-hmm.
So yeah, I guess I mean, we need to think it more deeply for such problem.
Yeah, definitely. And I'm submitting this for publication right now. Preprint might come out soon with some code. And I mean, this could be something that, you know, once that's all out there, that might be something you might want to pursue if you want to build on top of this work.
Sorry, just one more thing to add. We can still add something like synaptic plasticity to such a problem, and I don't know, maybe we can with combining all of this idea came up with one single neuron that can extract features from the data set, and with the aid of synaptic plasticity, it can fire more. With higher frequencies or lower frequencies to classify a 10 classification. You know, but I'm not sure. I'm just guessing all of this.
Yeah. What synaptic plasticity would replace in this model would be some form of the back propagation algorithm that allows for the weights to change upon receiving some loss information or incorrect or error information. So synaptic plasticity would replace that, and instead it would, depending on whatever plasticity rule you're using, you can then change the weights that way. However, that might be disjoint from the idea of 10 class classification. I feel like that has more to do with the type of output that you're allowing the model to have. The type of output this model is allowed to have is the nonlinearity on the output node is a sigmoid activation function, which which maps all of the outputs or the sum of the inputs that it receives between 0 and 1. and it would then learn to either produce 0 or 1, or something close to 0 or something close to 1. Now, if you were to, say, remove that nonlinearity or replace it with something like ReLU or something else, it could be unbounded, and perhaps then it can then, with some sort of loss function, learn, okay, 0 to 1 is class 0, 1 to 2 is class 1, 2 to 3 is class 2, and so on. And perhaps that could be another way to train. Now, I'm not sure if that would train well. It's something that you can try.
And the bottom line is I'm a fan of redundancy, the brain, and that for that matter, I think the single neuron classification is a cool subject for awesome presentation.
Thank you for your awesome questions.
So I have a question, if I may go next. Okay, so as you showed in your figures, I mean, the graphs that you showed comparing the different tasks and how well the one tree fared among, I mean, it's probably the next, or not this one, the next one. Yeah, right. So in these graphs, I kind of felt like I saw something like the learning happening quite fast in the first part, and then reaching kind of something like a plateau, which happens in humans. I was a bit curious, I mean, how that works out. Is there a saturation point after which learning isn't working out that well, or would that be something like that?
So yeah, so the learning process that each model, so the x-axis for this corresponds to the model architecture, which is set in stone once training or learning begins. And yes, as you increase the size of that architecture and the number of repeats, it approaches some plateau of learning, or learning only gets so good at a certain point. Now, the length of time of learning is determined through what I call an early stopping algorithm. So in deep learning, there's you train the model based off of how close it is in getting everything right, or how wrong it is as the inverse. And in that loss of how wrong it is calculated, and when the change in how wrong it is reaches a plateau that is quantifiable, I stop training, and that is when I do a final accuracy check, which produces these data points. So when the neuron model is no longer learning, or is no longer learning, that is when I determine what the accuracy is on my test set. So in a way, you can see that there is a bit of a slowing down of how well it learns as you increase the number of repeats. But I would say that the takeaway here is that it does increase. Now, I do not know if I can address the part which is this what happens in humans? Given the
it happens in humans. I mean, learning happens quite fast at the first part, and I mean it goes pretty fast, and then it reaches a plateau. That's how human learning works. So that's why I was curious if
Yes.
this is very similar to how humans learn. So it was very fascinating to, think about it.
I think I understand your question better more now. So not depicted in this slideshow are what we would have a loss function. So I was talking about loss before, how wrong the model is when it is seeing new data and classifying it. And basically at the beginning of training, it's very wrong, and then it quickly becomes, the loss function where it's very, very wrong up here, and then after a few cycles of learning, it drops tremendously, and then it plateaus. So yes, the learning curve, that's what we would call this loss decrease. The learning curve does drop precipitously in the very beginning, and then plateaus as training goes on until it reaches a final plateau where it does not change, and then training is ended. So just like in humans.
Thanks, that answers my question.
Then I had one question. So you already mentioned it in your limitations and the future work that this abstract modeling it is not like always correlating to what the biological phenomenon actually is. There are some discrepancies. So I would just like to pick up on what Nosratullah was saying in terms of biological constraints. So he mentioned synaptic plasticity as one. So I was thinking that these single neuron computations, do they take into consideration the local graded potentials, the potentials which do not actually propagate, and they tend to remain localized in certain places like the neuromuscular junctions or the receptors, for example. I mean, how does these single neuron computations, account for, how are they present in that scenario? So what goes on there in that case?
Yeah, so given the nature of the model that I'm using, it's very abstracted, so it doesn't really have those pieces built in. If you were to try to add those things in some way to this model, then you might be able to then learn how those things might impact the model's performance. So that's a good question. Trying to understand how these different aspects might, that's the kind of thinking that I'm trying to, that I think is really cool, which is how might this property impact performance? And that can be done by building a model with that particular detail. And then learning how that detail impacts performance is something that you can track.
Right. In this case, you mentioned that there is this binary condition. There is this all or none law, but like the graded potentials, they don't take that into consideration. So that's why I was thinking how different it can be. If there is no consideration of all or none principle, then how does this computation changes at the single neuron level? So that is what I was trying to think. Yeah. Cool.
Yeah. So those credit potentials. I actually haven't heard them described as credit potentials before, but if I'm understanding that correctly, it's basically, like dendritic spikes.
Yeah.
Is that correct? Yeah. So those kinds of things could potentially be represented in a recurrent model. So where if you were to look into each of the nodes of this recurrent neuron model, you might be able to see through its time-varying recurrent dynamics that there could be, some form of, credit potential-like signature. But I want to say again that the nonlinearities in my model, and it's not depicted as limitations and assumptions, but one of the limitations is that the nonlinearities in the model that I use are not like the dendritic nonlinearities that are seen in real neurons. So whether or not you see something like dendritic spikes will probably be determined by what types of nonlinearities are built into your model. So if you wanted to go in that direction, you would likely take this model that is trainable and able to do a particular task, and you would have this dendritic sparsity constraint, you would have recurrence, and you would have realistic nonlinearities, not just leaky ReLU, but perhaps something that looks more like the IV curves, or the current and potential curves that represent the nonlinearities that exist in real neurons.
Cool. Thanks, Ilenna. Thanks so much.
Thank you.
I think we don't have any more questions.
Mm-hmm.
Yeah, so yeah, I think we can conclude the presentation now, and I would just like to say that it was an amazing presentation, and I'm also new in neuroscience, and I could relate to your examples that you gave, and it was very, very informative for the audience.
That's great. It's great.
Thank you for the presentation. And do we have anyone else?
All right then.
Feel free to, if you have any further questions, I will paste my email into the chat. I realized it wasn't in my presentation, but feel free to send off an email, ask me if it comes up, save that if you like. I can also be found on Twitter. You can DM me on Twitter. And thank you for having me. This was so much fun. I really appreciated all your great questions. And feel free to keep sending me more. And keep in touch. I'm going to continue on this general line of questioning with my work. Mm-hmm.
Yeah.
Thank you.
Thank you.
I'm just going to read the chat real quick because I didn't read the chat at all. But yeah, thank you.
Thank you.
And thank you to all of you, actually. So it was really nice to see a lot of known faces from actually Twitter as well, and also much more exciting to see newer faces, actually. So yeah, cool. And we hope to see you for further meetings as well.
Thank you for attending, guys. Bye-bye.
Yeah, bye. Thanks.
Bye-bye.